Hello, I am Taylor Paraiso, and in this video I will be discussing what limits endurance performance. Now, an athlete can train for hours on end, but they will always ultimately reach a point of exhaustion, wherein their body is no longer capable of doing work. Why is this? Even the most elite endurance athletes will experience exhaustion and will have to stop activity. But that point at which this occurs for the athletes is unique to the physiology of each individual. Therefore, our objective is to learn the various physiological factors that limit endurance performance. The very first topic I will be discussing is energy and fuel. Now, how is energy made and used? Well, adenosine triphosphate, or ATP, is the main energy currency of the body. It is produced via metabolic pathways from glucose, which is the primary substrate of ATP production. There are several metabolic pathways. One of them is glycolysis, which occurs without oxygen, and the second is oxidative phosphorylation, which occurs with oxygen. Glycogen is a form of stored glucose in the muscle, which can be broken down via glycogenolysis. Now, ATP is used by binding to binding sites within the thick filaments of the muscle fiber called myosin. Hydrolysis or breakdown of ATP supplies energy for myosin heads to release the thin filaments called actin. The myosin heads reposition themselves and reattach in a new position along the actin, and this completes a muscular contraction. What happens when fuel sources are depleted? Well, the body is unable to make ATP. And when there is no ATP to supply energy to myosin for release of actin, we stay in a state of contraction, which is not an optimal state to keep the body in. Therefore, energy and fuel is an important limiting factor. Bergman et al. Found that decreases in glycogen concentration has an exponential relationship with exercise intensity. As exercise intensity increases, more energy stores, such as glucose from carbohydrates and glucose stored in muscle glycogen, are consumed at a faster rate. Glucose in the blood travels through circulation from the inactive muscles to the active muscles at sub-maximal levels of intensity. Some examples of fuel sources. Riddle et al. Found that carbohydrates ingested during exercise contributed to the most energy production for both male and female endurance athletes. Fats were the second most useful in the production of energy, and blood glucose levels also consistently deplete during the initial stages of endurance activity, then eventually increase again after 45 minutes, likely due to the breakdown of ingested carbohydrates. The next topic I will be discussing is VO2 max and running economy. So what are VO2 and running economy? VO2 is the rate of oxygen consumption in units of milliliters per kilogram per minute. Running economy is the rate of amount of oxygen used when running a constant given running speed in units of milliliters per kilogram per minute. And energetic cost of locomotion is the amount of oxygen needed to cover a distance in units of milliliters per kilograms per kilometer or liters per meter. Now, VO2 and running economy both show how much oxygen is being consumed during endurance activity. VO2 max is the maximum rate of oxygen consumption. And this can help athletes understand their endurance performance. For example, it can help them determine how economic their running style is. Economic running would have a lower VO2, and uneconomic running would have a higher VO2, wherein you are reaching your VO2 max at a much faster rate than if you were an economic runner. The relationship between VO2 max and energetic cost of locomotion was found by Shaw et al., and they found that VO2 max and energetic cost of locomotion have a linear relationship. So as VO2 max increases, the energetic cost of locomotion also increases. Conversely, running economy and energetic cost of locomotion are very different from each other. Fletcher et al. Found that while the rate of oxygen consumption increased with increasing speed at lactate threshold, the oxygen consumption over that distance did not change. Additionally, the VO2 max stayed the same over all speeds, and only the VO2 increased. Therefore, a training goal that endurance athletes would have is to find a way to reduce VO2 so that it would take them longer to reach VO2 max, and they'll have overall better endurance performance. The next topic is thermoregulation and osmolarity. So how does thermoregulation relate to osmolarity? Well, osmolarity refers to the concentration of molecules in a solution. In this case, we are referring to sodium concentration in the blood. Dehydration is the lack of fluid ingestion, and hyponatremia is a condition where there is low sodium concentration in the blood. Thermoregulation refers to the body's ability to maintain its core body temperature. So when the hypothalamus in the brain detects an increase or a decrease in body temperature, it sends signals to the body. When it senses an increase in body temperature, it will activate cooling mechanisms. An example of one is sweat, which is very beneficial in hot and dry climates because it will evaporate on the skin and leave a cooling effect to bring down the body temperature. Whereas it's not as effective in humid climates because it will just drip off. So large amounts of fluid intake and a high sweat rate actually contribute to the development of hyponatremia in athletes. Barnes et al. Reported that a sweat rate of 1.13 liters per hour was associated with a 41.7 millimole per hour loss of sodium. And this is very bad for the body, as sodium is an important cofactor for metabolic processes. So when there is low sodium concentration in the blood, the body will not be able to produce energy, and it will result in the onset of fatigue. So to go over some research surrounding this topic, Xu et al. Observed that endurance activity in hot, humid environments led to higher heat energy storage, which caused a decline in lower muscle group power output, and the body does this to compensate for the increase in heat energy storage. Nettle et al. Reported that a 15-year-old male developed hyponatremia following consumption of 1.9 liters of fluids. Additionally, there was no change in caloric intake during the marathon, so he was not consuming any electrolytes, and electrolytes include molecules such as sodium and potassium that are used as cofactors in metabolic processes. And as a result of his large fluid intake with no intake of electrolytes, he developed hyponatremia, where he had a low blood sodium concentration of 134 millimoles over liters following the marathon. The next topic I will be discussing is the heart, brain, and muscle fibers. So there are several models to understand endurance performance. The first is the cardiovascular anaerobic model, which states that endurance performance is limited by the onset of anaerobic or no oxygen conditions. And this is because the capacity of the heart to pump oxygenated blood is limited, and thus the VO2 max is also limited by this capacity. The second model is the central governor model, which states that the brain monitors the rate of oxygen consumption as well as the level of oxygen in the body. Now, as the body reaches its VO2 max, there is less oxygen that is being supplied to the body, and the brain can detect this and recruit less muscle fibers as a result. And this causes the onset of fatigue in the working muscles, and it causes the onset of fatigue before the heart can fatigue, ultimately preventing the heart from being damaged. So to give an example of both the cardiovascular anaerobic model and the central governor model, Bigland, Ritchie, et al. Observed that contracting muscles reach a point of ischemia, which is a state of low oxygenation, and this is associated with a decline in motor neuron firing, as well as the onset of fatigue. Additionally, firing rates remain low until the muscles are no longer ischemic. The third and final model is the muscle power model, which states that muscle fibers of individuals differ in contractile properties due to its composition of tissue, such as the elastin affecting the elasticity of the muscle fibers. And this affects the ability of the muscle to contract and generate force. An example of the muscle power model was reported by Laturco et al. They reported that endurance athletes have contraction times of 22.9 milliseconds, while power athletes have contraction times of 18.8 milliseconds. And so this is because power athletes and endurance athletes differ in their fiber type and their overall muscle fiber composition, which supports the hypothesis that the muscle fiber composition has an impact on the muscle contractility of an athlete. So overall, the limiting factors of endurance performance are nutrition, primarily carbohydrate intake, because carbohydrates are the fuel source that contribute the most to energy production, the maximum rate of oxygen consumption and how economically this is used, the ability of the body to maintain its core body temperature, also known as homeostasis, and along with this and its cooling mechanisms to maintain that homeostasis is fluid and electrolyte intake to prevent the development of hyponatremia. So all in all, we can conclude that the main players in limiting endurance performance are the heart, the muscle fiber, and the brain. So these are my references, and thank you very much.